So now this is hopefully at this point of the course, hopefully you will be able to design op amps. I guess you are already doing it now. So now it turns out just after doing the schematic design, things are not over. So this lecture I thought I'll give a brief, on what happens typically after, let us say, you design your op amp, right? What all you have to, and the first thing you have to do is basically something called layout. That is where you become a civil engineer and decide where each block is going to be placed and how connections are going to be made. And let me give some tips as to how to do layout, right? Again, doing layout is not a really great value addition. Anyone can pick it up at any point, but what is important is how to do good layout, right? So that's what I wanted to briefly talk about. Okay. Let's take an example of this inverting amplifier. So what is the gain here from V out to V in? -2. What is setting this gain as -2 exactly? Negative feedback, but okay, fine, true, but the ratio of these two elements, right? So essentially you have to make sure the ratio of these two is exactly 2. That's what determines it. So let us say, let's look at how to lay out the two resistors. So let us say this is a resistor. I draw a rectangle using something, and then I have twice the length, and this is one way to get 2 times R. But it turns out in practice we already know that this is not going to be a pure rectangle. This is going to be something record shape. So this will also be something. So which means we can't guarantee that if I have 2 times long, this will exactly be 2 times R. So what do you think might be a better way to make 2 times R? I mean, let's say you have 1 chocolate, your friend has 2 chocolates. You also say, I want 2 chocolates. What do you do? Huh? I mean, you basically have 2 of them and connect in series, right? That's the best way. So instead of doing this, you basically put 2 of them in series and say this is 2, this is better. Right? So that's the fundamental thing. If you want to have something to be scaled version of something, you basically have multiple items and put them in series or parallel. That's a fundamental thing in analog layouts. And now the other question is, can I, let us say, have the R resistor to be horizontal and the 2 times R resistor to be vertical? Do you think this is better, or keeping all of them in the same orientation is better? At least logically it makes sense. Keeping them in the same orientation is better, because again, remember, we want to have identical things. If this is R, this should be exactly R, and this should be exactly R. So you try to keep the same orientation for all of them. So you don't do this. Instead, maintain the same orientation. Okay. Now, other thing is, this is a minor thing. So it turns out this is via basically, right? You, from the resistor to make contact onto metal, you put some pillar. That's called via. In practice, you don't put one via because it can may or may not make good contact, so you put multiple vias. Okay. So let's say I don't show this via now. So this is R and 2 times R, right? So now become really become very obsessed with this, have a lot of OCD, and tell me, is there something that is different for the resistor here and the resistor here? Ignore this connection. I mean, let's say these gaps are, I mean, spacing is same, but if you want to be really obsessive, do you think something is different for this fellow and this resistor? What is different? I mean, okay, that's fine. Location will have to be different. We can't do anything. But I mean, look at this. The middle one in the middle resistor and the corner resistor, right? Yeah, this guy is surrounded by 2 similar resistors, whereas the corner ones don't have any neighbors, right? So to make this guy also feel comfortable, what do you think we can do? Yeah, you basically put some 2 resistors on either sides. We call this dummies. You basically make sure the same ambience is there for all resistors. Same environment is there for all resistors. See, I mean, this is, I don't know, stupid analogy I think of is, if let us say there is a birthday, if a kid has a birthday party and the kid gets all the presents, and if the kid has a very small younger sibling, the parents, what they'll do, they'll give a small dummy gift to the baby so that baby doesn't feel bad, right? Same thing, to make sure that this corner guy doesn't feel bad, you make sure, oh, this also sees a similar environment on this side. See, the idea is everything should be identical. That's the idea. and this is basically dummy. It is not contributing anything in your actual circuit. You basically short it and don't do it. So now other thing that can happen is the following. So as of now, this is your R and this is your 2 times R, correct? Now in practice, it turns out there can be linear gradient. This can happen in each step of the fabrication process. You guys might be already taking IC Fab course. From each step, starting from ion implantation, etching, blah blah blah, can have a linear gradient. Or let us say maybe here there is some big circuitry here burning a lot of power. So temperature at this end might be higher than the temperature at this end. So the resistance value can actually change. And as usually, we'll assume a linear gradient. So this can be R plus delta R plus 2 delta R. Now do you think the ratio of this is exactly 2? No, correct. So now what do you think we can do so that the ratio is exactly still 2? I have 3 resistors, R plus delta R plus 2 delta R. Is there something I can do to make sure that the ratio is still exactly 2 even though the resistance values have linear gradient? Correct? Yeah. So what he's saying is you connect these to the corner ones, put them in series, right? So something like this. If you put them in series, the effective resistance now we have is 2R plus 2 delta R, which means the single resistor now is R plus delta R. So now even though there is a linear gradient, if you take the ratio, it's exactly 2. Right? So that's the idea. And I mean, this, if you actually think about it, the basic principle is simple. You try to make sure that all the elements have a common centroid. Your high school geometry principle, right? So if there is a linear gradient, extreme ends can change a lot, but the middle point doesn't change. So that's how you do it. And you can extend for any ratios. For example, if you want to have R and 4 times R, you make sure that the middle one is the single element and the corner ones are put in series to get 4 times R. Right? And of course, at the extreme ends, and this can also extend for 8 times R. So again, this will be R. Here you have 4 times, here you have 4 times, and you put them in series. But if you do this, now you see that the spacing from the resistor at this end and this end is going to be really large. It turns out the relative mismatch, in addition to being inversely proportional to square root of area, it also is dependent on the spacing between the elements, physical spacing between the elements. So instead of spacing them in a 1D array like this, in a long 1D array, to make the spacing short, what can we do? I have 9 elements totally, right? Instead of placing in, as of now, I'm placing them in one particular row. I gave you the result. One particular row, having lot of spacing. To make it shorter, you basically put it in a 2D. So this way, the spacing on both dimensions is actually small. The hope is that the variation will also be small. And again, you make sure the common centroid principle is followed. The middle one is the single element. The surrounding ones are the 8 times R. So even if there is a linear gradient, either in the horizontal direction or vertical direction, any linear gradient on both sides will get exactly cancelled, because on both x and y axis, this is the common center. And as I mentioned, you make sure that the corner guys don't feel bad, because they don't have neighbors on the other end. So what do you do? Yeah, you actually put a dummy like this. Of course, you can also put dummies here. I didn't show it for the sake of space. Now, if you are even more considerate, you see that, hey, this dummy does not see, So, if you want to be really obsessive, you can even put one more layer, but doesn't help so much. But that's it. If you are really obsessed and really matching is really critical, in sometimes this is also done. So,
capacitance.
Same.
The resistors might have capacitance due to.
That is something you cannot do. That's something you can't avoid. You have to deal with it. Right? So to summarize the basic techniques to follow in layout. Anytime you want to have, scaled version of an element, you don't have a long or a wide element. You have multiple elements put in series or parallel to get the scaling factor, and you make sure that you place them in the same orientation. And you don't have a single via, so that the contact is proper. And as I mentioned, you make sure dummies are added so that all of them have the same environment, and you make sure that all of them have a common center. And if you look at the price you have to pay for doing the first 3 things, there is no price we are paying. It is almost for free. So there is almost no reason why you should not be doing it like this. So these three things are absolutely critical, essential you have to do in a layout. Now, if you are adding dummies, what is the penalty that we are paying? More area, right? That's the price we are paying. Now, if you do, in addition, if you try to do common centered, what do you think might be the price we pay? Hmm? I mean, basically, it turns out the routing can become complicated because now if I have, something like this, and if I say that these two have to connect in series, now I have to connect them like this, and this is the center one. Center one has to come out, so you have to do all these things. So routing can become tricky, but of course that's the price you pay for getting better matching. So this is the order in which you keep doing. So you first three things you definitely do for sure. Now depending on the extent of matching you want, you either do one or both. So that's what is done. So now this is for resistors. Same thing happens, same thing holds good for capacitors. So now if you look at transistor, same idea. Let us say you have a current mirror. Again, I have one transistor, 1x width and 2 times width. So how do you think I will realize this 2x width transistor? I try to put two of them in parallel. So something like this. This is, let us say, the transistor with the size of 1x. This is a transistor with the size of 2x. As you see, I have shorted the gates, shorted the drains, and shorted the source. Now it turns out for a transistor, if you want to get a width of 2, there are two things you can do. So here you actually see that I'm putting two of them in parallel, but these two drains are finally getting shorted. So instead of having two separate drain junctions like this, what do you think we can do? I have two drains getting finally connected. So instead of having two drains and connecting them, what can I do? I can overlap and say that, not overlap, I just have one drain and say that's a common drain for both. So that's what is sometimes done like this. So in practice, if we have two of them put in parallel like this is called as having multipliers. Okay. Whereas if you share the common junctions and use a shared junction, that is called as having fingers. I don't know, because apparently someone thought this looks like two fingers pointing up, so they call this fingers. And yeah, in practice, if you have a multiplier, that better mimics an exactly 2x multiplied device. But if you share junctions using fingers, since the number of junctions is reducing, the parasitic capacitance associated with each junction will also reduce. So this is more compact and has lesser parasitic. And in practice, we use a combination of both multiplier and finger to realize a given particular width. So I'll show it an example now. So for example, let us say you want to realize a total width of 12 micron. So usually we don't use a single transistor whose width is exactly 12 micrometer. The reason is simple. It turns out if you the transistor models we have, they can deviate if you use a really large width or really small width. So the usual thumb rule is we use nominal widths, for example about a micrometer or so. So the single instance we usually have a micrometer or 2 micrometers at the max, and then use fingers or multipliers to get the required 12 micron width. So if you do this, the total width will be the number of fingers times the number of multipliers times the unit width. So I'll show it an example again. See, again, if you take this example of 12 micro, so I can do something like this. I can have 12 fingers like this and put them like this. But here, if you see the transistor at the left end and the right end, they are spaced far apart. As we already know, if they are spaced physically far apart, matching cannot be so much. So what do we suggest we can do? You have a 2D structure. So that basically means I'll have a 4-finger structure like this. As you see, 1, 2, 3, 4. This is a 4-finger transistor. I'm putting 3 of them in parallel. So 4 fingers and sort of 3 multipliers, and I have to connect them finally. So basically I have to short all the gates, and then all the sources have to be connected, all the drains have to be connected, and so this way in practice, this is how you sort of make a wide transistor, not a single instance put spanning the entire x-axis or y-axis. You try to keep them compact so that the matching is better. For that you use a combination of multipliers and fingers. And again, whatever we saw in the first half still holds good. So the transistors at the corners here, they'll feel bad because they don't have neighbors here. So what do? You put dummies and introduce neighbors for them, something like this. Now remember that these I put an, I mean, if you clearly see, what I have done is I had 4 fingers here. Now I added 1 finger on either ends. So this is now your dummy transistor. And this dummy transistor should not contribute anything in your actual circuit. So what do you think I should do to the transistor? I have dummy transistors placed with gate, drain and source. I don't want this to do anything in my circuit. So what do you think I can do? Yeah, I can basically short all of them. Something. So this way it will not do anything in the circuit, but at least its job is to make sure that it provides same environment or ambience for the corner or extreme ends of the elements. And in practice, there is also a consideration on, let me show it this way. See here, to get 12 fingers, what I used was 4 fingers and 3 multipliers. But what is something I could also have done? I could have done 3 fingers and 4 multipliers. 4 times 3 is same as 3 times 4. So, but in practice, we prefer having even number of fingers for the following reason. If we have even number of fingers like this, now you see that this structure itself has a common centroid. Correct? So again, any linear gradient in this direction, that gets averaged out. So that is one of the reasons why we prefer having even number of fingers rather than odd number of fingers. And again, this is not really strict. If possible, we try to use even number of fingers, but if not, for example, if your total width is 9 micro, can't do anything, you have to probably use 3 by 3. So again, to summarize, for transistors, same principles, use multipliers for exact replication. But in transistors, we can also share junctions to save area and reduce parasitics, and that's basically called fingers. And in practice, as I mentioned, you don't use a single instance with a really large width. Use, let us say, a micrometer or so, and then have a combination of fingers and multipliers to get the final desired width of whatever you want. And the final thing to take into account is, if possible, try to use even number of fingers. That way, the structure will have a common centroid by default. So it basically helps with averaging out any linear gradients. So again, this is the order in which we try to do. So I would say at least this much is definitely needs to be done. The last point, you try to do if possible. Good. So now let us say you have done the transistors, laid out the transistors, you connect them. So once the layout is done, do you think the design is done? No, unfortunately not, because there are a couple of things. You have to do something called as a design rule check. This is where the foundry will have some conditions saying that if I have a metal connection like this, I need to have a minimum spacing between another metal connection and stuff. And similar lots and lots of rules will be there so that it can be fabricated properly. You make sure your layout follows those rules. That is something to be taken care of. Second main thing is to check if whatever you have laid out matches what you have designed in schematic. So that is called as layout versus schematic. That is basically looking at the two and finding 6 differences between them. And if there is differences, you go and correct them. Right? That's all. And the next step is the most critical thing, which is called parasitic extraction. Again, to just brief on this. See, let us say you have a simple common source like this. Again, this is supposed to be connected to VDD, but let's say this is small signal ground. You have a transistor, you have a resistor. Now in schematic, you'll draw a nice wire like this and say it's nicely shorted. But in layout, you'll put a metal line and make this connection. Now, metal line is not an ideal short. Has some resistor, but it turns out as you if you are interested in higher and higher frequencies, if you have a line like this for very high frequencies, how can you model a line like this? Yeah, it's essentially like a transmission line. You have to have a distributed effect. So it is not a single R and a single C. So you have a distributed RC network like this. and the number of RC sections sort of will increase if your frequency of interest also increases. Right? You might have seen in transmission line courses, so similar principle here. So which means even though ideally you want this to be a nice shot like this, the moment you short them in layout, it is not a nice shot. It will have this kind of distributed RC section. So you'll have all of these Rs and Cs, they are parasitics. They are like parasites attaching to your circuits and sort of modifying your actual circuit. Right? So you have to extract these parasitics, and there are multiple levels of extraction. One, you see extract only the capacitors. That is, you assume that the resistors are 0. So you basically say that in this connection I have an extra parasitic capacitance from that node to the ground. Now the second level of extraction is, along with this capacitance to ground, you also include the effect of coupling capacitors. For example, you had a connection like this, you had another connection like this. This is connecting to some other line. Between these two there will be a coupling capacitor. Include the effect of this also and extract, and then see what happens in your circuit. But the ultimate check is this: include the distributed RC, all the resistors, capacitors, and coupling capacitors. So include this, and you have to basically check the circuit. And if you do this right, see earlier when I didn't have this distributed RC, I just had connection like this short. How many nodes I had in the circuit? If I directly just short it, how many nodes are there? 2 nodes. What are the nodes? I mean, I'm shorting N1 and N2. Okay, ground is there. Okay, this and one node. But let us say now, if I include the distributed RC now, how many nodes are there? There will be so many nodes, right? So which means earlier, let us say your circuit, let us say had some 10 nodes. After extracting all the parasitics and including this distributed RC, the number of nodes will actually explode like anything, right? So if the number of nodes increases in the circuit, do you think the computer will take more time to solve or less time to solve? Why? Huh? Yeah, I mean, how do you think computer solves circuits, simulates circuits? Huh? Yeah, what matrix? Yeah, I mean, how do you solve circuits? KVL, KCL. So for using KVL, what should you do first? You have to find loops or something else. It is not loops exactly. What is it called? Meshes. For finding KCL, for applying KCL, what should you do first? What should you find? Yeah. I mean, for KVL, you have to recognize how many meshes are there. For KCL, what should you recognize first? Nodes. You think recognizing and finding number of nodes is easier or number of meshes is easier? Why? See, I mean, you should be able to answer for every possible question, right? Only then you understood it. Why do you think? Yeah, I mean, the moment you define an element, that element is connected between two nodes. That node is defined, whereas mesh is not easy. So, do you think computer will be using KCL or KVL? KCL, because that is the easiest thing. So, computer will use KCL, and in KCL you can basically write a matrix like this: G times V equal to I. Right? Now, if your number of nodes increases, the size of the matrix increases. So the simulator has to invert this G matrix. So inverting a matrix is already a very complex task. If the size of the matrix increases, this will take much longer time. So in practice, it is not uncommon to have like a practical analog mixed signal system. If you extract all parasitics, the simulation can run for several days or sometimes even a week. So it is not uncommon to have situations like that. Yeah, so as I mentioned, because of this, the simulation time actually can grow crazily. But turns out, let us say your design works after including the effects of all parasitic, resistor, capacitor, and coupling capacitors. Do you think the job is done? Why not? It turns out, fortunately, the job is not done yet because you have few more things to account for. The problem is this. Let's say this is your actual silicon. The silicon die is very brittle, it will easily break. So you cannot use it directly. So what do you do? Yeah, all the ICs you see have a plastic coating. That's basically a package. The silicon die is packaged on a plastic, whatever encasing, so that it can be used in proper electronic systems. And this is your the white one is your actual silicon die. Now the blue one is the plastic package. So all the connections we have to take it to the package here like this, and this has to have a really small resistance or a large resistance. So what do you think we'll use for this? If you want to have the smallest possible resistance, I mean, okay, let's say I give you all money in the world. What would you use? Gold. Yeah, gold is that's what is used. That's why I used this color also. And in practice, gold is what is used, and that's why in China people sort of take old chips and sort of melt it and try to extract gold from it and make money, right? And of course, it turns out the money you spend in trying to get the gold and the gold you get, they are hugely disproportionate. It is not a viable business. But anyways, so now we have long wire like this, and because of gold, let us say the resistance is going to be small. So what will this wire contain because of this wire? If you have a piece of wire like this, a long piece of wire, is it a short circuit or something else will be? Or let us say simplest model is what? I mean, resistance is small. Single line, let's say we have a metal line like this. What will it have? It's an inductor. I mean, in practice, both R and L, but gold will have really small resistivity. That resistance is negligible. So it will be an inductor. So finally, this is how your circuit will look like. Let us say this is your actual chip. This is the connection to the pad. You are thinking you are feeding the input directly like this, but unfortunately, no. There is a big inductor sitting between your circuit and you, and trying to modify the circuit. And typically, this can be of the order of 1 nanohenry per millimeter. So which means you should basically take into account the effect of this bond wire inductance also. I mean, by the way, these are called bond wires because they are sort of bonding, uh, the connection. So you have to take into account the effect of these bond wires also and simulate it and make sure your design sort of works. If not, you have to do things here and there to make it work. And one trivial, I mean, let us say one trivial way to reduce the inductance is this. I have 3 of them put in parallel. So then the inductance value becomes what? 1/3. So this is one trivial way, but if I do this, what am I losing? Yeah, space, but even more fundamentally, I mean, I have so many pins is what I can do. Now for one pin, if I am dedicating 3, I will not have sufficient pins. So which means if I want to accommodate all pins, I need to have a bigger package. Now with the bigger package, if you have, the inductance value itself will increase. So you can't do this crazily. I mean, it's not. Finally, they will basically. I mean, it is very difficult to already bond a single wire from here to there. So it is. I'll show you a picture, then you'll understand. So that's not done. If you want to do, you do it this way. So which means, this is the picture I was wanting to show. This is, I don't know if you can see. So this is a chip that I taped out some time back, and this is the actual silicon die, and you can actually see the gold wires sort of connecting here. So here, if you see, I have basically placed the silicon die closer to the left side. So what can you say about the inductance value on these sides? Smaller. That's exactly the reason I try to place these pins on the closer to the left side. But what is the downside in keeping it to the left side? Yeah, other side will have a longer inductance, right? So that's the trade-off. And this is another picture. This is from extremely old IC. I don't even know who designed it. So you can even see the layout more clearly here. And the bond wires are all already messed up. So as you see, even to keep one wire, it is actually tricky. So that's why this is a problem. So which means it is not sufficient if your design just works at schematic level. Now remember, even at schematic level, we already saw there is process voltage and temperature variation, right? So the process corner we already discussed, supply voltage can change and temperature is an obvious factor. So first of all, it should work across PVT in schematic level. Then you do the layout, and with parasitic extraction, it should work across PVT. But that alone is not sufficient, because as we saw, when you package it, you have these package parasitics. So for including, I mean, it should finally work at finally this level. Only then a circuit is actually ready to be used in practice. Otherwise, it is sort of useless. It is just an academic exercise, nothing but a simple file in a computer. So that's why I usually give this. Let us say you have a perfectly working design, but it works only in one corner, and no parasitics, and then you think that I have designed an excellent IC. After tape out, this is what you'll have. You'll think it will work nicely, but exactly it will come and poke you where it didn't work, because it will come at some corner, it will work at some temperature. All the package parasitics will mess you up. It will never work. Right? So this is something to. Right? So that is why this entire business of designing chip and make sure that it finally works as a usable product in practice. The entire thing is actually a work of art, right? And as I mentioned, right, see, uh, with post layout parasitics, the simulation in practice can run for several hours or several days in practice, right? So that is why you can't say that, hey, I don't know what this transistor does. Maybe I'll change this transistor with maybe 3-4 times. I'll run 10 different simulations and wait. No, then you have to wait for 10 years. It's not going to happen. So that is why if you have a circuit, you should have a clear understanding of what each transistor does in that particular circuit, right? So only then you will know, if let us say in my final system this specification is not met, what transistor to go and tweak, and what should I tweak in the transistor, whether I change the width, length, or change its GM, blah blah blah. So that kind of understanding is absolutely essential for a skilled analog designer, because in practice we cannot rely on running iterative simulations. It's not like running a code. Oh, this is not working, I'll command this line, run it. Oh, it's not working, okay fine, I'll change this variable to this. No, something you cannot do. Similarly, let us say you made a mistake, you cannot do a backspace or delete and then correct it, right? So that is not at all possible. And that's exactly the reason why I have been emphasizing on deriving and synthesizing circuits from scratch. Because it's easy for me to just show the circuit and then tell this is what the circuit does, this is the small signal gain, blah blah blah, and I'll finish my time easily, right? But that will not help you, because maybe you can remember 2-3 circuits, but not more than that, because human brain, fortunately or unfortunately, is not good at remembering a lot of random things. But what it is very good at is understanding some logical sequence of steps and solving a problem, right? And uh, that's the nice thing about circuits, right? See, you don't have to sort of remember a lot of things. All you have to remember is KCL, KVL, V is I times R, Q is C times V, and a MOSFET current equation. If you know these 4, you can solve any circuit in practice, right? So this is unlike some other subjects where you have to remember this equation in this regime, this equation in this regime, and then after 5 years they will say this theory is wrong, we'll come up with a new theory, it's a new equation, now you remember this, right? So that's something that will not happen here. And in fact, if you open any analog circuits textbook from 1960s also, you'll find whatever I taught, almost all of them might be there similarly. Minor circuits, minor changes might be there. The only change will be that the transistors in the old textbooks might be different. They might have vacuum tubes, bipolar junction transistors, JFET, MOSFET now, then FinFET, ABC FET, XYZ FET, some random FET will come. But doesn't matter, because with respect to small signals, a transistor, how does it behave? Voltage control. That's all. Because see, remember, what is a transistor? Why is it called transistor? Yeah, it's a resistor. So it's basically trying to change the resistance, which means you want to make a switch. You want to control the flow from terminal, let us say A to terminal B, using voltage applied on another terminal C. This is essentially controlling the current through a voltage. So fundamentally, you are making a voltage controlled current source, right? So if you understand how to make circuits using voltage controlled current source, you will always stay relevant even after 10-20 years. If a new transistor comes, the same circuits you can use with minor tweaks here and there. Right? So that's why I jokingly say sometimes that all the hey, come, yeah, come, yeah. You can sit. Yeah. So Professor Arnab will take the SRS after this. Yeah. So that's why I jokingly say sometimes that all the movies and childhood stories you would have heard growing up might not be very socially and culturally relevant, because we would have evolved a lot. But what will always stay relevant is the tale of a voltage controlled current source. So even after you grow old, you can tell your grandkids, say, look at this is a voltage controlled current source. You connect this way, you get an amplification. So yeah, that's the nice thing about circuits, right? See, and personally for me, I grew up at a time where there was a huge IT revolution, right? And when I was studying, when I was in my undergrad, I always wanted to be a programmer. So I was an avid coder, learned C, C++, Java, C Sharp, .NET, everything. But one thing what I recognized was, when I moved from one language to the other, I completely forgot the syntax of the previous one, right? I had to remember a lot. But then I learned electronic circuits. First, I was taught BJT, common emitter, whatever, and then I was taught common, MOSFETs. Then I find BJT, MOSFET, hey, it's same. I don't have to remember a lot, right? That's so nice to me, right? And for me, the first wow moment in circuits came when I sort of related signals and systems I learned in second semester to a circuits course I learned in my third semester. So in signals and systems, I learned that Fourier told centuries ago that if I have a square wave, how can you decompose it as summation of sinusoids? And in circuits course, I learned that if I have a RC circuit, it acts like a low pass filter filtering sinusoidal frequencies. So that made me think, what if I pass a square wave through a cascade of RC filters, RC sections? I tried that on a lab during a lab session. I find that square wave input, sine wave output. It was a warm on for me. Right? And that is something I never experienced with coding. Because when you're coding, you are actually telling the computer what to do. Right? If the computer does what you tell it to do, there is no element of surprise. You will be surprised if it's not working as you expected. That's when debugging starts. Whereas with circuit design, that's not the case. You are actually working with basic principles and fundamentals. There is always a possibility of experimenting and trying out new things, coming up with new circuits. Right? And this, in addition to the fact that there is enough number of high-paying jobs in circuit design, made me choose IC design finally. Right? And as I mentioned, see, when I was growing up, it was IT revolution. But right now, you are at the inflection point of semiconductor revolution. Right? As I mentioned in the first class, 10 years back, if you told that you are a chip designer, they'll think you are designing uncle chips or less chips, right? But now everyone sort of knows what chips are, right? And that is why you are at the right point, the beginning of the semiconductor revolution. So this is I will say, the right thing to do. So anything related to semiconductor, chip design or anything related to this field is the best thing you can do so far. Right? Sorry. And the other thing I would say is at this point you should be really proud of the fact that you are sitting in this class right now. Because if you are sitting in this class right now, this is a second level circuits course, right? Which means you have taken one analog circuits course before during your undergrad or EE 210 for UGC here. Which means you would have taken a circuit analysis course before that, a signals and systems course. And to learn all of that, you will require fundamentals of calculus. And that's what your entire 12 years of schooling trained you for. So which means the fact that you are sitting here is not because you prepared overnight and came here. It is years of consistent effort and practice has made you come and sit here. So bottom line, IC design is one field where the barrier to entry is very high, right? That is important because there are a lot of fields, emerging fields, not emerging fields, a lot of fields now where they will say, you do this short-term course for 2 months, you'll become an expert in this field, you can get better jobs here, right? There is nothing wrong in doing that, but there the barrier to entry is very low, right? So which means there you will find that if people will be 10 years experience in one field, they'll do a short-term course, switch to a different job role and get jobs. Completely fine. But if you are able to do a short-term course in 2 months and switch to a new job, so will be 10,000 others, which means you are not really a valuable asset to a company, right? So that is why it's crucial to make sure you are specializing and building your expertise in a field where the barrier to entry is very high, which means you will be a valuable asset to the company. You can't be replaced so soon, right? And the moment you are sitting here means that you are already kind of crossing the barrier. You are already in mid-air like this, right? So this is the barrier to chip design, and you are sort of in between. So you cross the course, you already create a bigger barrier. See, yeah. So there is nothing wrong in choosing profiles where the barrier to entry is low, but you guys are the top people here. You have in IIT Kanpur, so you should not settle for something that is lower than your standards, right? So I would say in future, anytime if you are building your expertise or career, try to choose and steer your career in a direction so that you are becoming an expert in a field where the barrier to entry is high. That's what will guarantee you a better job, in the industry. And IC design is one field where barrier to entry is high, and of course, make sure there are enough number of high-paying jobs in that field, right? And this semiconductor field is one such field where you get enough number of jobs and barrier to entry is high. So that's basically what I wanted to tell you to motivate this course. Typically, motivation is given in the first lecture, but I sort of feel it should be done in the last because in the first class everyone is ultra motivated. Everyone, you want to learn classical mechanics, quantum mechanics, rocket science, everything in the world. Only when the semester becomes the middle, then you feel this is worth doing. Can I drop the course? Towards the end, you're like maybe I'll skip the end semester. So that's why I wanted to motivate at the end of the class. So hopefully you are motivated enough. You'll do your you'll be doing. I hope you do your project well and do your end semester. So I think that's all from me. So I think I'll stop the class here. So Professor Arnab will conduct the SRS feedback now.
The last class?
Yeah, yeah. I finished. I took extra classes in the beginning.
You will also tell me to do this.
No, I've taken 26 lectures.
Oh, okay.
See, other thing is, today is the last lecture.